I guess people will trickle in shortly, but we can start with Orit Raz on rigidity. Thank you.
Okay, so indeed I'm going to tell you about graph rigidity. I'm going to define everything, and then I'll try to get to some newer results. So I'll start with a basic definition. So we have a graph, an abstract graph, and we're given an embedding of this graph of the vertices in Rd. So endpoints in Rd. And the general question is the following. Let's look at this graph. Say it's E3, and it's P1, 2, 3. And what we want to understand is whether we can find another embedding of the same graph close to the original one. So let's say this is P1 prime, P2 prime, P3 prime, that induce the same edge length. So something very close to the original one and has the same edge length. The general question is, fine, or does there exist? It's dangerous to say, can we find? Not in the computer sense. So does there exist? An embedding P prime close to P that induced same edge length. So of course the answer is always yes, because we can always just shift a little bit the original embedding or rotate it a little bit and we get the same thing. But the point here is we want to know whether there is a closed embedding that gives the same edge length but not congruent to the original one. So not congruent. Okay, so this is the question. And for example.
Oh, what you mean? Isometry of the whole space? What do you mean?
Yeah, so there is. So I will say it more precisely later, but you can think of it as in a triangle. It's a bit redundant, but instead of only having the same edge length, having the same distances between every pair of points. So. So you want something that preserves only the edge length, but then can you find the P prime such that not all the pairs, the length of all the distances between all pairs are preserved. But it's the same as having an isometry of Rd that maps P to P prime.
So if you look like at two path, like you can think about it as a clock, right? Like where you can like move the two.
Right, this will not be right. So I'm not going to give examples. So yeah, so this is not rigid in the plane. Rigid in R1. Some examples. So dimension is 2, so we're in the plane, and let's say that G is a triangle. Let's take this embedding, 1 square root of 2. So now can we find another embedding with same edge length that is not congruent to the original one? No, right? Well, this is the only way to draw this triangle. This is rigid in R2. And what about, so this is, if G is C4, let's look at this embedding. And in this case, you can find another embedding. All edge lengths are 1, 1, 1. And it's not congruent to the original one, so this is not rigid. Or flexible. Okay, so I'll try to stick to it now so that I
Really, the physical intuition is whether you can, if they were made of metal rods and they had flexible joints, if you could
Right, if you
push
can just,
them or screw
right.
them or to change the shape.
right. Okay, so let me give the formal definition for this. So I call a pair a graph and an embedding. We'll call it a framework. And so we say that a framework or GP is a rigid framework if there exists a neighborhood of this P, this neighborhood such that for every other embedding P prime in this neighborhood, if P and P prime induce same edge length, then in fact they are congruent in prime congruent. So either you can think of this as having an isometry of RD that maps P to P prime, or so this means that distance or the length of the IJ edge, so the distance between Pi and Pj is the same as Pi prime to Pj prime for every IJ in E. We use the same edge length. We want this to imply that Pi minus Pj is the same as Pi prime J prime. It's same for every IJ, not necessarily in E. So the set of vertices, sometimes I will call it V, sometimes it will be the numbers 1 to n. Okay, so this is the definition of a rigid framework. Right. So two natural questions that arise when you look at this definition. So you might ask first, how do I check? To check whether GP is rigid framework. Another thing is that when we look at those examples, it looks that it's not really a property of the embedding. Like if I take a triangle, so there's nothing very specific, very special about this triangle. So any other triangle that I was maybe 1 and 1 would still be rigid. And any other, so not every embedding of C4, so there is one embedding of C4 that will be rigid, but other than that, it looks like that in general, this thing is flexible or not rigid. So is it in fact a property of the graph G independent of the embedding? So it's rigidity. In fact, G, meaning without the embedding. Yes.
This C4, you're really embedding into the line, right? Even though you're putting it in.
Right, but with other graphs you can have, this will not be the only examples where it's not that it is a lower dimension. I'll show more. So you're right that this is degenerate, so it's not a generic one. But then the generic ones do not have to lie on a lower dimensional space.
And a priori it's also not clear that it's a local thing and not. I mean, I can think of an example where you don't really need this neighborhood thing. Only it's like
right. So sometimes you don't need the neighborhood thing. So this would be called global rigidity.
okay.
But there are examples where you do need them. For example, here. So locally, you don't have anything that is close and not congruent with this one, but you can flip one of the triangles. And you get the same. Okay. So how to start to analyze this? Again, I want to stick to my notes. But if I want to lose time, okay. So, good. So one thing that I forgot to say here is that, so we have these isometries, and one way to get rid of them, if it bothers you, the fact that they are congruent copies, so we can always, if we want, consider embeddings of the following form. So we can take the first point, embed it to the origin. The second point, we can force it to be on the x-axis. PD. And now all the other points are free, go wherever they want in RD. And if we consider only such embeddings, then we don't have two congruent copies that are not the same. So if we only restrict to those embeddings, then the question can be, if they have the same edge lengths, then they are the same embedding. Okay, so sometimes it's easier to think about it like this. Okay, so just as a note. And now I want to go back to these two questions. So one way to start analyzing this is by looking at the map. So consider the map FG, RD to the N, RE. Or if you want to look only at these embeddings, so it would be from R, D, and minus D plus 1, choose 2. Again, just as a side remark. And what this map does is it takes an embedding of G in RD and return the edge length. So Pi minus Pj squared, so this will be a nice map, so polynomial for every ij. Fix some ordering on the edges. Okay, so in terms of this map, the rigidity question is is more or less, is this FG invertible, locally invertible? What do I mean? You give me the edge length, and I want to be able to go back to the embedding, right? This is what we're trying to do. Okay, can I go back from the edge length to know what the embedding is? So now it looks more analyzable. We have a function, we want to know if it is locally invertible. We know what to do. It's a very nice function. It's a polynomial function. We can look at its Jacobian, right? So this is the Jacobian. G, and we can see that its rank is at most Dn minus Z plus 1 choose 2. Because in the kernel we will have all the isometries, or if you think about this as our domain, so of course the Jacobian, this is the number of columns of the matrix, so you cannot have rank more than this. So this is the maximum it can get, and by inverse function theorem, we get a sufficient condition for a framework to be rigid. So if the rank, the Jacobian at P is Dn minus P plus 1 choose 2, then GP is rigid. Okay, so this is sufficient condition for a framework to be rigid. So this is stronger than being rigid, and this stronger thing is called, GP is called the infinitesimally rigid. Let's double S. Okay, so it implies rigidity of a framework. But the nice thing here is that the rank, the maximal rank of a matrix is actually a generic property. So if we find an embedding where the rank is this, then we know that for generic embedding, the rank will be this. So this allows us to define a rigid graph independent of the embedding. The definition would be, so G is rigid in RD if for every generic P in RD, the framework GP is rigid. This is rigid.
What do you mean for every generic? If it's for some generic point, then it's for all generic points.
Right, so it's equivalent to say there exists.
Is it clear to everybody why it's
What is generic?
So you can say for every embedding other than, you need to throw a algebraic variety of lower dimension, or you can say that the coordinates of the point are independent over the rationale. So kind of
in our world, this is just a condition is a determinant basically. It's a polynomial condition. So it vanishes only on some lower dimensional variety. So it's basically a PIT formula, a special case of PIT formula, where the parameters, the variables are the coordinates of the embedding.
right.
And generic is anything not on this variety.
Right. And so Asimov and Roth, I think they made order in all this theory, and so on. They showed that that this is indeed if their generic rank, because if the generic rank is less than this number, it might still be rigid in principle, so there is something to show. So that rank J, F, G, P equals D n minus D plus 1 choose 2 for every or for some, every. So this is actually equivalent to being rigid. The generic rank really tells you whether G is rigid, the graph G is rigid. Okay, so let's see some examples again. So in dimension 2, and let's graph G, let the graph G be K33. K33, we know that in general it is rigid. So K33 is rigid in alpha. What are the infinitesimally rigid embeddings of K33? So those where the Jacobian has the correct rank, the maximal rank. So it is infinitesimally rigid if and only if the vertices P1 to P6 are not embedded to a conic section. So do not lie on a conic section, a curve of degree 2. On a conic section. So if they do lie on the conic section, the Jacobian will not have the correct rank. So it will have a smaller rank. But still it might be rigid there, and indeed, so K33 P is rigid, a rigid framework. So if and only if P1 to P6 do not lie on a pair of perpendicular lines. And I mean, 3 points here, 3 points here, and the edges are between them. Okay, so this is the only embedding where the framework is not rigid. But for all these embeddings, the Jacobian will not tell us anything because the rank will be too small, but in general, it is rigid.
Maybe it's a good idea to just to work with Jacobian. I mean, it's very simple.
I will.
Explain why that's not rigid.
Yeah, so I don't want to lose time by finding, I can, during the break, I'll try to find, but there is a very, very simple motion that shows you that these distances are preserved, but you don't get Conjecture copies. So I can really write the formula. I might spend half of the, okay. Yes.
In the definition, we say that the graph is rigid if for every generic P it is rigid.
Yes. It's equivalent to for some, but yes.
Right, and you say it's equivalent for some. So now in this example,
Yeah, so the graph K33 is rigid by definition because for generic embedding, it will be rigid.
I see.
But the framework, so now you look at the specific embedding and you want to ask whether in the neighborhood of this embedding, you can find a copy with same edge length, but not congruent to the original one. So now we're like, we really care about this specific embedding.
Yeah.
And here the answer is, as long as the points are not embedded too. So you can check the Jacobian there, and it will tell you that if the embedding of the points is such that the points do not lie on the conic section, then you're safe. But if they do lie on a conic section, you cannot apply the inverse function theorem. So it might be.
If the 6 points lie on a cycle.
Then Jacobian will not give you the right number, the rank of the Jacobian. But it is still rigid.
But why do I care if you told us that, it's enough to find 1 point, right? So I can just put them in.
It's a matter of taste. So if you only care about whether the graph G is rigid or not, then you know the answer. But I sometimes care about specific.
I understand. I'm just trying to understand whether this was supposed to prove to us that it's rigid or not, and if not.
No. So I'm trying to say that the Jacobian does not give you everything. So there's still some. If you care about specific embedding, it's still a hard question. But if you care about the generic one, then you know the answer.
Okay.
But in the definition, you said.
So this is the definition of.
It's equivalent to there is a framework which is rigid.
Right. This is the definition of a rigid graph.
Yeah, then the framework should be rigid in strong sense, not in that. Right.
Yes, because if it is infinitesimally rigid, then it's also rigid.
Okay, it's rigid. Okay.
If the Jacobian has the right rank, then it's also rigid because of the inverse function theorem.
Yeah.
If it's not, it might still be rigid. It's always the direction.
You put the points in a conic section or in a cycle, there's still a general position, something degenerate.
So I don't say general position, I say generic. So this is maybe, it connects to your comment from before.
So can you define generic?
Yeah, so the coordinates should not depend, should not satisfy any polynomial equation with rational coefficients.
Not
transcendental numbers, if you want. There's transcendental numbers.
If you take 6
equations, it's also polynomial equations that are not allowed.
If you take 6 points and ask whether they lie on a common conic section, you can write this condition as equations with rational coefficients, and generic 6 points will not satisfy us. Will not lie on a common conic section. So this is a special choice of 6 points.
I see. Okay.
So
now
I understand the definition, but I no longer have intuition for it.
You can think random. Think about the random.
Yeah, random.
Think random with high probability. That's enough.
No, but random, you can think about a lot of other properties random points have, and maybe if this doesn't capture them.
Well, it's, this is true for PhD course.
I mean, you take these points on the cycle, you move one just a little bit, or maybe you need to move all six, but just a little bit, right? They will not lie on, I think they will not lie on any.
Yeah, if you move one, if you run the position, it would be.
Right. So that's why I'm.
Well, in this case, it's a particular graph.
Right, of course, but what I mean is that you move some points like you ask them a bit, I don't know, apply some option noise. You don't expect them to satisfy anything.
Yeah, and they want, yeah, that's true. But then,
Sure,
I mean, greater than?
I understand.
Ah,
All you're saying, I understand. What I'm saying is that I don't understand.
tell them your point, otherwise they will be on a quadratic.
it's actually,
Oh, it didn't.
it's serious, it's not just you, the 100 years
It's
of
rigid,
work,
okay?
still don't understand. It's not what you're getting, I mean, really.
No, it's okay.
It's actually more than 100, it's Lord Kelvin thought about it.
Okay, so complete biproduct graphs in RD. So in general, if you have enough vertices on both sides, then they will be rigid. So Kmn is rigid, as long as this and this is whole. But the rank will be smaller, and Walker and Roth show exactly when it will be smaller than dn minus d plus 1 choose 2, exactly when the n plus n points lie on a quadric surface of degree 2. Quadric surface.
So you didn't put a name on the first one, it means that it's.
I think it's relevant to both. They also
Oh.
also implies. I don't know if it was known. So. Question. And so this is about infinitesimal rigidity, about the rank of the Jacobian. And if I care about actual rigidity, rigid. So it should be some subsets of the embeddings where this Kmn is not rigid, should be a subset of this. Because if it does not lie on a quadric surface, then it's rigid, because it's also infinitesimally rigid. But if I care about actual rigidity, then this is open. So we don't know. You know, if you put n plus n points on a sphere, is it in fact rigid or it's really not rigid? We know it is not infinitesimally rigid, but it might still be rigid. And this, we don't know.
Yeah, but the graph itself is rigid.
But what?
Yeah.
Yeah, generically,
If you have enough
if you have enough, yeah. But generally you are. Also, we know exactly what embedding, you know, we know infinitesimal rigidity exactly. We have a full description, but for actual rigidity.
I think bipartite graphs are interesting because they don't have triangles, so it doesn't, you know, triangles are clearly rigid with triangles. But or the simplest in general.
Okay, so now we know it's a property of the graph, you know, for generic embeddings, and you can ask.
Is there any kind of explanation of this d plus 3 over 2 plus
Yeah,
1?
it's the dimension of the quadric surfaces. You know, if you have this number of points, then there always exists a quadric surface that lie on all of them. And this will mean that it is never infinitesimally rigid, so it's never. So this is exactly the. Okay. And so we know it's not, so now we know that it is a property of G, and we want to ask, can we give a combinatorial description? So we look at the graph G, we don't really want to write the equation, the matrix. Can we say, can we give a description in terms of the graph in order to know whether G is rigid or not? So combinatorial properties of rigid graphs. Then I'm going to look at the matrix in order to understand these properties. So let's look at the Jacobians. How does it look? So we have, for each row, we can associate with an edge of the graph. And each D columns will be a vertex. So I have D columns for the ith vertex and D columns for the j vertex. And in this coordinate, I will have Pi minus Pj. Pi is the embedding of the vertex I, and Pj is the embedding of Pj. And here I will have Pj minus Pi. I have it this times 2 bits and zeros. So this is how the matrix looks like. And I know the way we should think of it is as following. We have the embedding. These are the unknowns. So we have dn or dn minus d plus 1 choose 2 unknowns. And whenever we add an edge, we add some constraint. So you say, okay, let's look at all the embeddings where the distance between this point and this point is 2. This is a subset of the embedding. So whenever we add an edge, we add constraint, and we want to add enough constraints so that it fixes the embedding. Okay, that's how we look at it. So what do we know?
Just to clarify, this Pi minus Pj is a vector of length d, the
Right.
distance set in every coordinate.
Right. Yes,
Blocks are length d,
right.
and down the end.
Yeah, so Pi is a point in Rd, and Pj is a point in Rd, and this is just like the direction. Okay. So what can we learn from this? So we know that the rank, wait, it went out. So we know that the rank should be dn minus d plus 1 choose 2 in order for this to be rigid. And we know that, if we have some such metrics with this rank, we know that we can always find some subset of the rows where we have this, the same rank, dn minus d plus 1 choose 2. So it's always enough to use exactly this number of edges. So let's define G to be minimally rigid. Rigid in Rd. If, I don't know, I write it like this, if G is rigid in Rd, and also the number of edges, G is exactly dn minus d plus 1. And now let's try to characterize those graphs that are minimally rigid. And for those graphs, there is a obvious necessary condition for G to be minimally rigid. So this time, okay, so the number of edges should be exactly dn minus d plus 1 choose 2. So we have exactly the right number of constraints, so we don't want any dependency. We don't want to waste any constraint, right? So when do I waste a constraint? If I have a small set of vertices and I put here too many edges. So those vertices don't have that many degrees of freedom, and if I wasted some edges here, I will have here dependency, and then I will have dependency in everything. So the necessary condition is that if we have a subset of the vertices, and we look at the number of edges when we restrict to this subset, so number of edges in G restricted to this subset, it cannot be too large. It shouldn't be too large. So it should be at most D times the size of this subset minus D plus 1 choose 2. Okay, this B prime should be at least D. Okay, so we should not have too many constraints on a small set of vertices.
This three, the d plus 1 over 2, first you used the first d vertices or something. Now you may use other vertices. So it's still, the fact you subtract d plus 1 over 2. It still intuitively sounds right, but I don't see why.
Why I subtract this?
No, in the lower line, here.
Here?
Yeah, because the vertices are not necessarily the first vertices as well.
No, it's not related.
It's just that if you restrict this matrix only to the edges of GV prime, right?
Yeah.
Then you look, so all the columns of the vertices that are outside of V prime will be 0. So it will be like a smaller
Yeah, but the
submatrix of this that will
number of
correspond.
columns is more than what you wrote.
It doesn't
number
matter,
of
the
what?
number of rows will be too large in this subset, and so it will have to be dependent.
Yeah, but the number of columns is not.
It doesn't matter if the number of columns is larger, you know that there are trivial degrees of freedom because of the isometries. And you are in RD, so this will be the.
Yeah, no, it's nice intuitively, but okay.
It's like, so you should have complained here when I said that the rank is always at most this. So if you have n vertices, the rank cannot be larger than this. If you believe it here, then here it's just like a subgraph, and n is now the size of V prime, and it's the same. So it really, formally, if you look at the metric, it's just the matrix Jacobian of FG, where G is now this subgraph. Okay. So this is a necessary condition. Yes.
So you define the minimally rigid here as like counting the number of edges satisfying this condition is this necessary. Is this equivalent to saying that like if I remove any edge from G, it will not be rigid, or is that like a different?
It should be equivalent.
It's going to be equivalent.
So definitely one direction is zero. So if it's minimally rigid, when you remove
An edge.
an edge, yeah. And what is the other
It's like
direction?
if and only if.
So what is the other direction? If you have a graph where you remove, I don't see the other, but if you have a minimally rigid graph, it is true that whenever you remove one edge, it will be.
Okay, I guess I'm more asking in the other direction.
So what is the other direction?
Like if I take a graph and it's rigid, but removing any edge makes it not rigid, is
Oh,
it then minimally rigid?
Yeah, and you have too many rows if you.
yeah, it's exactly like linear algebra.
Okay.
You know, you have dependent vectors in RDN. So if one of them depends on the others, then removing it will not change the rank. But if you know that the rank is exactly the number, so it's just like linear. Okay. So this I consider as, I mean, definitely it's a combinatorial condition. I just need to count edges, vertices. So it's some description in terms of the graph. And it turns out that for dimension 2, this is also a sufficient condition. So let's call this counting necessary condition star and the theorem of evening. So Hilda Geringer. So she did it in 1921, but later in the 70s, Laman. Something like this, and they show that for d equals 2, this counting condition is if and only if G is rigid in R2. Okay, but the idea of the proof idea, at least Laman's, I don't know.
Can you explain what the theorem means?
It means that if you have a graph and you want to know whether it is minimally rigid in R2, then this graph should have exactly 2n minus 3 edges.
And be rigid.
And
No.
for every subset of k vertices, the number of edges on this subgraph is at most 2k minus 3.
And that's it.
And that's it, and then it's rigid. Okay? So it's just like you look at the graph, you count edges, vertices, and you know it. Yeah, you forget about the matrix, you forget about everything, so they show that it's equals 2, it's the same. You just need to do this counting. And the way they proved it is by showing that this counting condition that we just did is in fact equivalent to being able to build G by starting with an edge and adding one by one vertices of degree 2 or 3. Never mind, I will not. So G can be constructed. I will not give the details now. I will say something later that will give some details. Constructed by adding with some rule vertices of degree 2 or 3. So the counting condition is equivalent to this. The one thing that one needs to show, and then they show that this is actually equivalent to being rigid with R2. So if G is rigid in R2, it can be constructed in this way by starting with an edge and adding vertices of degree 2 or 3.
What
And if-
edge lengths are you gonna use?
So for generic edge length. So now it's a
First, you choose generic edge
No,
length.
you don't need to, so now it's a combinatorial.
You build a graph, there are no edge lengths. You're building a graph.
Yes.
All you are given is a graph.
You start with this, you add a vertex of degree 2. Now if you want to add a vertex of degree 3, you need to delete one of the edges. And you do this, do this, you get a graph, an abstract graph. This graph is rigid in R2, generically. For a generic embedding, this graph will be rigid.
So you have to delete it.
Then what are you
Fine.
doing? You're adding and deleting, but what are you?
Okay, so anything in the, so I didn't describe the steps.
When you say
The
add,
statement-
the
the statement is the following. This conditional sparsity of edges in every subset is equivalent to saying the graph can be constructed in a particular way, starting from an edge.
I can say it, okay.
It just, it's a statement.
Okay, let me describe you a family of graphs, okay? So any graph in this family is a graph that was constructed in the following way. You start with an edge. So this is G2 because it has 2 vertices. Okay, and now I want to go to G3. In this case, I have only 2 vertices, so the only way to go to the G3 is to add a new vertex of degree 2. So you add a new vertex and you connect it to 2 existing vertices in the graph. In this case, there's not much to do. So we have to be G3. And now G4, you have 2 options. Either you add, so you have G3, and you add a new vertex. And now you can do whatever you choose to do. Either connect it to a pair of vertices in G3, you can choose which one, or you delete an edge and you connect it to 3 existing vertices. 2 of them are the ones that the endpoints of the edge that you deleted.
You delete it.
You
to
do this
preserve the
sequence.
condition.
What?
You delete the edge to preserve in order to preserve the condition.
Right,
of the
right. So this is a process. You can get
So you generate all possible graphs with this.
So it turns out that whenever you do this, you generate a graph that satisfies the counting condition. You also generate the rigid graph, and vice versa. If you have a rigid graph, it can be constructed in this way. And also, if you have a graph that satisfies the counting condition, it can be constructed in this way.
Thanks, okay.
Okay?
When you add a vertex of degree 3, I am a bit confused which edge you are erasing.
So you can choose. So you have GI, and now for a GI plus 1, you choose any edge, any existing edge. You delete it, and then you connect the new vertex into the endpoints of the edge that you removed, and any other third vertex. Okay? I'm glad that you're asking about this because I'm going to prove something that's like about this step. So it's
So
okay.
basically, like you gave us now an algorithm for enumerating over all rigid graphs in R2.
Right, yes.
And now you just need the induction to prove that if GI was rigid and J plus 1 is rigid, right? This is what
Right.
you show
So
us.
you need this and you need also this if you, but yes. Right. So I will actually show this part because, because of the number of edges, you look at the average degree. So you always have a vertex of degree either 2 or 3. So you need to show that when you remove it, you preserve rigidity, and when you add one. I think you'll be able to. You'll be able to do this, but okay, I'll show. I will prove a lemma that talks about this step. Second.
This unfortunately is called Laman's theorem.
It's called Laman theorem, but yes, right, even though you did it before. And,
Well, these things can be changed, you know?
yeah. I'm trying, but I was
Right,
forgetting how to spell last time. Yes.
Does this also imply that G is infinitesimally rigid or just like?
So if a graph is rigid, it means that it is generically rigid, which is equivalent to the fact
Oh,
that
yes,
they
okay,
were
right, this
leading.
is about graphs. not
So a generic embedding will be infinitesimally rigid.
Right,
Yes. A specific embedding might
try not.
either be or. Okay, so before I'm talking about this adding a vertex, degree 3, I just want to tell you the disappointing part is about higher dimensions. So we have a combinatorial characterization of rigid graphs in R2 by this theorem. But what about higher dimensions? So already for d equals 3, we have an example called the double banana. So in this example, so this is one banana, two bananas. So this graph satisfies star. So it has the counting condition, but so satisfies star, but not rigid in R3. Satisfies star, but not rigid in R3.
So you can rotate it around these two vectors.
Right. So you can rotate it around this. So it's not rigid. Okay, so we know that for d equals 3, star is not equivalent to being, so in d equals 2 it's the same, but in d equals 3, star is not equivalent to being rigid in R3. But it still might be true that being rigid in R3 is the same as constructing G in some way, but by adding vertices of dimension. Instead of 2 and 3, it will be d plus 1. But so maybe this thing can still be generalized to either dimension. So this was a conjecture of Graver. So Graver's conjecture. Graver's conjecture. Again, I'm not being precise here, but if you're going to be upset at me, I will be more precise, but I'm not. So, so maybe G is rigid in RD if and only if G can be constructed by, so you start with KD, start with KD, and now add vertices in a specific way so that it's a bit more technical to describe exactly how, but and add vertices one by one of degrees d plus 1 up to d2 d minus 1.
Wait a minute. This counterexample suggests something else, right? It suggests that you had you removed two vertices and you made it disconnected. So perhaps
we need another. If you have a suggestion of potential,
no. I mean, this is if you do it in every dimension, right? You take d minus 1 vertices which disconnect the graph. Then you always have. So I mean, you can guess another. There's another natural guess, which is you also don't allow such a.
I like this question because maybe it will give us another. Okay, so tell me later, okay?
But it's clear that you have to be deconnected. Yeah. But just a counterexample.
It will not be,
Yeah.
it will not be sufficient to be deconnected.
Yeah.
So there are
That's what I
examples.
say that you perhaps you need.
But it is,
More counterexamples to.
well, but it shows that the counting is not. At least this is how I always
Yeah.
say. But I mean, it shows that the counting is not true, but it also like suggests maybe this error. So this is why I'm. But about connectedness, so I will mention some new results about connectedness. So if the graph is connected enough, it's true that it is rigid, but it's not. It's not a condition for minimally rigid graphs. Okay, but so this is what Garver conjectured. So this turned out to be false for. So this is false for D at least 4. And the counterexample, again, I didn't prepare it, but you can come up with this example if you look at complete bipartite graphs. It's not so hard. And open for D equals 3. So for D equals 3, we have some, at least a candidate for a combinatorial characterization of rigid graphs, but for D 4 and up, we don't even have a conjecture how to characterize that.
Maybe it's good to talk about complexity in terms of what is combinatorial. We know rigidity is an NP, that's obvious, and because you can find an assignment that makes the rank. We don't know if it's in prime. We have no idea even.
Which arrow is incorrect?
So good question. So if you want to add, so already for adding a vertex of degree D plus 2, it falls for D at least 4. So if you want, you have a rigid graph, you want to remove 2 edges. And so this is in our, in every dimension. And then you want to connect a new vertex to these 4 vertices, plus as many vertices that you need in order to get D plus 2 total. This will not, so G was rigid and the new one will not necessarily be rigid.
So it could be that all rigid graphs could be constructed by this way, but maybe you need to impose some additional conditions so you maintain rigidity.
So, okay, so if you are rigid,
But you're talking
you can
about.
go down, so you can be constructed this way.
Yeah.
But if you're constructed this way, it's not necessarily, that does not necessarily mean that you're rigid. Yes.
But here it's only about minimally rigid, right? Not in general.
Right, but every graph will have a subgraph that is minimally rigid and as exactly the same.
Yeah, but you can have a like bipartite with huge degrees, I mean, or.
So give me the title first. Are you complaining about something, suggesting, or I'm not?
No, I think that the conjecture doesn't make sense if you take the complete graph.
Complaining.
Oh, if you do this, no, if you do this and follow the rules, so I didn't give the details how to add.
Okay.
If you follow the rules, you don't get more edges than what you need. You will get the right number of edges, but you will not have the counting. So for subset, you might be too dense. But you will get D times N minus D plus 1 choose 2 edges. Okay, wait, let me show you a lemma. This. I mean, I'm not moving to the next step. Still on this, so you will have the opportunity to ask more. But so okay, so lemma. So I want to show you that to add a vertex of degree D plus 1, it works. So if we start with a rigid graph, we add a vertex of degree D plus 1, then the new graph will be rigid. Okay? So G is rigid in RD. Let's do it in R3. It will just be easier to say specific. It's the same proof. You'll see. And do this 4. And let V1, V2 be an edge. Okay, and now let G prime be the following graph. So we have G we had this V1, V2. We want to remove V1, V2, this edge, and add a new vertex W, connect W, D plus 1 for D equals 3 is 4. So we connect W to V1, V2, and 2 other vertices, V3, V4. And the lemma says that G prime, this is G prime, right? Okay.
Connect it to V4.
Then G prime is rigid enough. So it's a known fact, but I want to show you my proof because I like it. So this is why I'm proving this, okay? So this is a proof. So I want you to like that. So what can I say? Okay, so what is the proof? So we start with a graph. I mean, it's going to be a picture, but I hope you will. So we start with a graph. We know, oh, it should be minimally rigid. Right? Okay, we start with a graph. We know that we have exactly the number of edges and it's rigid in R3 and it's exactly the number of edges. And now we remove this edge. So we know that we have 1 degree of freedom because we have all the constraints for independence. So we now have a 1 degree of freedom. What does it mean? It means that I have here, once I removed this edge, I get some family, one-dimensional family of embeddings of the vertices of the graph. And each such embedding, so this is the one-dimensional family, each point is an embedding of the vertices of the graph that satisfy all the other constraints. So they have all the edge lengths that I need, except for this edge, I didn't give any constraint. So it's a one-dimensional family of embeddings. Okay? And now I want to add this new vertex W. So I pick some generic embedding of this W, and I have this V3 and V4. And now I want to add these edges, so I add more constraints. So I have all the embeddings that satisfy already the existing constraint, existing edges. And now I want to find the subset of these embeddings. Well, they also have a distance, so I add the W, it's a point in R3, so 3 more dimensions. But now I want the embeddings that satisfies that the distance between W and V1 is A, the distance between W and V2 is B, the distance between W and V3 is some number C. Okay? So far, I added only 3 constraints, but W is in R3. So any embedding here, no matter what the embedding is, I can always find a corresponding embedding for W that will satisfy these 3 constraints. Because a point in R3, it has 3 degrees of freedom. I give it 3 constraints, there's always a solution.
As long as it satisfies the primal inequality or something.
Right, but you will have an open set where it's and you start with something that it holds, and now you look at the neighborhood, so it's always. But now you have the 4, so you are still, so now we have a one-dimensional family of embeddings in RD of these, n+1 points. But now you added the 4th constraint. So now there are 2 options. Either this, so this one might be an actual constraint. What are the options? Either this thing is a real constraint, and then I will have only a finite number of solutions. And then this means that we find a rigid embedding, and we're fine. So we prove that this thing is rigid, the big graph is rigid. Otherwise, if it's not rigid, since everything is algebraic, this is an algebraic variety, so the other alternative is that if it's not finite, then it must be everything. Okay? Of course, they can be reducible components, but locally we'll have only one, and it will be everything. So now I know that I took a generic embedding for W, and I got that all the one-dimensional family of constraints of embeddings still satisfy all of my constraints. So what I'm going to do next is, okay, let's add another point, W prime. I know now that for a generic point, I have again 4 constraints. But I know that W prime is generic, and I know that the number of solutions again will be everything. But since this thing is one-dimensional, it will be the same subfamily of embeddings that satisfy the constraint of W. it means that I can now look at the graph that include W and W prime, and I will still have a one-dimensional family of embedding that satisfy all of these constraints, the ones that come from W and the ones that come from W prime. So since it's again the same family, so I can add as many points as I want. Okay, W1, W2, Wn. And eventually I will get here a K4n graph in R3 with one-dimensional family of embeddings that have the same edge length, all of them. But K4n is rigid in R3, and everything here was generic, so this is a contradiction.
When you add W2, you remove the same edge,
Yeah, so I fixed all the edge lengths of G after removing the edge. And this gave me a one-dimensional family of embeddings. And I want to use them and to add another W. So in principle, when you look at one of these embeddings, they satisfy everything. You give them A, B, and C. It already determines the position of the W. And then the fourth edge is now determined because you know W already. So I wouldn't expect it to have so many solutions because there is a real constraint here, but maybe like D, A, C is the same for every area. Okay, so because K4n is rigid in R3, R3, so contradiction. Okay.
It's very nice, but now I'm not understanding what was the significance of the edge that you removed.
So you could remove any edge, but because you started with a minimally rigid graph, it gave you exactly 1 degree of freedom. If this thing, so if you want to do the same and remove 2 edges and add a graph, then you get here something 2-dimensional, and this argument doesn't work anymore because you get different. You add them, you get different 1-dimensional thing, and then you cannot say that they are the same. Bring me back to. Okay, so I think maybe it's a good time for a break, but let me just. Oh, I didn't. No, I'm not going to give you a break, even though I want to, because okay, I'll I might do a break later, but let's just make sure that I say something newer. Okay, so this is about like trying to characterize rigid graphs in RD. So we don't know much. We have some candidate for D equals 3. They just said about 13 vertices, but for higher dimensions, we don't even have a conjecture, unless the one will have something. But so now I want to tell you about some recent results that show sufficient combinatorial condition. So the first is a result of Villani, who solved a conjecture of Lovas and Yamini. So Lovas and Yamini, they show that if a graph is G is 6 connected, 6 vertex connected, then it is also rigid in R2. And they show that this is best possible, so they gave an example of a 5 connected graph that is not rigid in R2. And so a theorem from about a year ago, so see, Rani said that
6 vertex.
6 vertex connected.
This is in R.
In R2. So they conjecture that for any dimension, if G is connected enough, then it should be rigid in RD. So this was an open conjecture. So this is from 1982 or something like that. It was open for a long time, and people were.
He's a friend of my parents, so I took a picture.
Okay, wait, I didn't state the result yet. Okay, so we showed that if G is D times D plus 1 connected, I mean vertex connected, then G is rigid in RD, and this is best possible. D times 2 plus 1 is best possible, so there is a graph. D times D plus 1 minus 1 connected, that is not rigid. Okay, so it was a breakthrough probably because people tried for a long time, and the proof is really nice, short, so I want to tell you about it. But okay, let's take a break. Let's take 5 minutes break, and then. Okay, so I want to prove, not to prove, but to show you the idea of the proof of Villani, that show that if a graph is D times D plus 1 vertex connected, then it is rigid in RD. So like the first step, we try to convince you that it's like very out of reach to understand what graphs are rigid or not, and we don't have a combinatorial characterization. So the fact that there is a proof here, and it's like very simple and elegant, like so such a clean condition, so this should be exciting. So the proof idea is the following. So we fix. So first of all, I need to give you some terminology. So we say G's. So terminology. So G is called independent if the rank of this Jacobian that we had before is exactly the number of edges. Just means that we added edge after edge, and we always got a new constraint, a new independent constraint. So we say G is independent, and the closure of G is the opposite, like adding everything, adding all the edges that are already a linear combination of the existing one. So it's just G union with all the edges that when we add them, we don't increase the rank.
The span of the road.
The span of the road, yes.
All the edges in the span.
It is such that, I don't know, I wrote like this rank of J, F, G is the same with the rank of J, F, G union E. You don't see it, but if you add this edge to the Jacobian of G, it's a new row, and it does not increase the rank. So it's like, if it's already a linear combination of the existing edges, you just add it to G.
Do I need the embedding for that?
No, it's a generic, you should look at the,
For the people who
with
don't-
variable.
Coordinates, everything is
You
generic.
don't,
Yeah.
if you don't like generic, it's much nicer to look at the coordinates of the embedding as variables.
Yeah.
They are variables, you work over the field extended with these variables.
Right.
Like n times d so I have n times d variables.
Yeah.
Right?
Yeah.
And
Yeah, you work over the field with these variables and the rank is defined there.
Okay, so we have a, so this is a closure of G. And, okay, so now we have a graph G, suppose it is D times D plus 1 connected, we can always, instead of G, we can look at the closure of G. You can add everything that, because it will still, if you add edges, it still stays connected, and since it's only the closure, you don't increase the rank, so assume that G equals the closure of G. So we need everything. Okay, and now the idea is the following. So fix an ordering of the vertices, V1 to Vn. And I'm going to construct a new graph G prime, a subgraph of G. Construct subgraph G prime subset of G. And I'm going to show you how to construct it. And the property that we have is the G prime is independent. So I add edges, and all the edges are independent rows. It's Jacobian matrix, such that G prime is independent. I don't add edges that I don't need, that do not add any constraint.
And this is trivial, you want to say that subgraph is large also.
And then I will show that this, yes, you're right, this will be the conclusion. But first I'm describing how to construct this specific G prime, so any G prime. So how do we construct it? So we have this ordering. So the ith step we add the vertex vi. And now we want to add also edges that come out from vi, a subset of the edges in the original graph G. So how do we do it? Let's look at all the neighbors. So Ni will be the neighbors of Vig intersection with all the vertices that appear before Vi in this order that we fixed. V1, V2, Vi minus. Okay, so all the neighbors of Vi, but those that precede it in the ordering. Okay, so I have here Ni, and I have here the vertex Vi that I am now adding to G prime, and I want to connect it only to vertices that are its neighbors in G, but precedes it in the ordering. Okay, so if this set Ni is of size at most D, so if Ni of size most D, then I add all the edges. Whenever I add a vertex of degree smaller or equal to D, these edges will have to be independent. I've said it before. Okay, so if I have only D neighbors or less to add, so I add everything. Okay, so I add the edges like this as in the picture.
This is because in the matrix it will be like a triangular part.
Yeah, you can look at it like this. I like to think of it as you have a point in RD, you have less than D constraint, you can always like find the embedding, but yes. And now what happens if Ni is of size at least D plus 1? So I have this Ni, I have here more than the vertices. So two options, if this subset Ni form a clique in G, so I have no extra, right? So all the edges are here in the closure already. So I don't have any extra degree of freedom. So I will be forced to add only vertex of degree D. If I will add the D plus 1 edges, it will be dependent. So if it's if the number of neighbors that precede it is at least D plus 1, there are still two possibilities. So if Ni, so G restricted to Ni is a clique, we just pick D neighbors, let's say U1 to UD, and add only D. And connect this new vertex Vi only to a subset of D neighbors. So if this is if it's a clique, and if Ni, G, and I is not a clique, so in this case we take Vi and we connect it to subset of D plus 1. D plus 1 neighbors that do not form a clique here. So if these do not form a clique, there is still 1 degree of freedom here, and we can kill this degree of freedom by adding a vertex of degree D plus 1. So if it's not a clique, I find D plus 1 that if everything is not a clique, I have a subset of D plus 1 that is not a clique, and then I add a vertex of degree D plus 1.
And then this missing edge will become part of the closure of this subgraph.
So you reduce the degrees of freedom by 1. It's not clear if it looks like adding an edge here, I don't know. It might be more complicated than this. Okay, so I give the description of how to construct G prime, and then also like try to convince you that this is independent. So by construction, G prime is independent.
Are you saying that you were greedy? I mean, can you? It's possible that you could have added more than this one, right?
Right, but this will be yes. And now the part that I'm not going to show, but what I did is that, so he computed the average degree the expectation of the degree, so how many edges you add for a vertex V. So I call it the G prime phi V. And you show that it
Well, what distribution?
what?
What distribution do you have?
Over the orderings.
Oh,
pi.
random ordering.
Yes, random
You
ordering.
didn't say one, yeah.
Yeah, we fix one. Yeah, okay, sorry. We fix pi somewhere here. And now you just take pi at random and you ask what would be the degree of, so each step, how many edges you would add. And you show that this is, so for each vertex you would add D, the expectation would be D. Okay. Yeah, and then from this concluded in the number, expectation of the number, and I'm just trying to think if it was exactly D or it was this, something of this flavor. And then then this implies that the expected number of edges in G prime is Dn. So this means this contradicts. So there is an ordering with more than Dn minus D plus 1 choose 2 edges, and a graph G prime that is independent. This is a contradiction.
So the expectation is dependent on the connectivity. That's why.
Right, so we did it. Yeah, I wanted someone to ask. Good that you have contradiction to G prime being independent. Right. So it looks like he almost doesn't use the fact that it's the fact that it is D times D plus 1 connected. Where he uses it is that he shows that if you have, he uses the fact that if you have a vertex of degree D times D plus 1 and all its neighbors is a clique, then you can remove this vertex and you still get a D times D plus 1 connected graph. He wants to remove vertices that their neighborhood is a clique. That's the idea. So in order to remove such vertices, yeah, so he shows that if you have a vertex, okay, so V is a vertex of G, and the neighbors of V is a clique, then G minus V is still D times D plus 1 connected, unless G is K D times something, something like that. So he uses the connectivity in order to remove vertices that the neighborhood is a clique. Why does he need it? Because he wants to show that there are enough vertices that will have degree more than D.
I guess all he has to come, I mean, in the what you described, the only problem is OIC if there are fewer than the neighbors.
Yeah, there might be fewer than D, and then you want to compensate only by the D plus 1. So you want to show that in the neighbor, so you want to have, to have enough vertices where you don't get a clique here for this. And use rigidity also to.
Connectivity.
Yeah, but use also, I mean, where is the rigidity comes exactly except for the, so he also uses this,
You probably also want that in the ordering.
I will go.
You want, at least, at the very least, you want high degree, so that in the ordering, like V will come after a lot of its neighbors, right?
Right, but, so even if you added only vertices of degree E, you would get almost this, but you'll get something slightly smaller than D. And you wanted it to be like Dn. So for this, you use the D plus 1. You want to show that you have this. You have enough of D plus 1.
Sorry for being slow.
You weren't here at the beginning, so.
But I believe that this I was able to catch up. But you have an algorithm how to extract some kind of iterative and independent subgraph of a graph. It depends on an ordering.
Right.
And this algorithm needs no assumption of the graph G. It always works. So the main statement is this expected value is bigger than or equal to D, and for that you need this assumption of D plus 1 connected.
wait, so you need, okay, so you can do this construction always. You need to know that the G prime will be independent in the sense of rigidity.
That's sort of by definition, no? I mean, the G prime, the construction always gives an independent thing, no?
If G is closed, yes, but okay, because you said it like,
You build it iteratively, so whatever I give it, I can give it.
yes, if G equals to its closure, then it's true that whenever you apply this construction, you get a graph that is independent, yes. Because you want to know that, I mean, if this distance is determined, then it's also an edge. But yes, and then you want to show something about the expected degree. And this is some analysis that Villani did in his paper that I'm not telling you about, and he showed that this is at least D.
But that's sort of the heart of the proof, and that's what the condition.
Right, but this is the idea. Like kind of now, after you do this, you can analyze this. You can check what is the, right? But the place where he used it, he assumed that you start with a graph G, where the closure of G, if you look at the neighbors of every vertex, the subgraph, the induced subgraph of its neighbors is not a clique. Because if it is a clique, you can remove this vertex, you still get a connected graph with fewer vertices. So we took the smallest possible counter example and then showed it. So this is where he used it. And other than that, he used the fact that every vertex has degree at least D times D plus 1. Okay, and use the
doesn't use connectivity, just a minimum.
just by
degree.
after removing these vertices, it doesn't use it.
I see.
And he also used some properties. So you want to know something about the number of cliques. So it shows that it uses some property of rigidity is that if you have in the neighbors 2 cliques, you want to look at maximal cliques. If those 2 cliques intersect in D minus 2, I think, vertices, and when you add this, you get 2 cliques that intersect in D minus 1 vertices, and then this will be a whole clique. So he wants to count the number of maximal cliques, so it uses some properties of rigid graphs there as well. But other than removing the vertices, it doesn't use connectivity. It's strange, but that's I mean, unless I missed something, this is how I. Okay. So again, you need to look at the details, but this is like really, this is the idea, now you need to analyze. Okay? Okay, so this is like one sufficient condition that I wanted to tell you about. And the other one, this is one.
But sorry, after you remove vertices,
Yes.
don't you affect the minimum degree of other vertices?
So if it's a clique, so I don't know, it's a lemma that one needs to. So if it's a clique, I mean, you can prove that the minimum degree stays the same by like just looking at the definition of D, of K connectedness. So if you remove K vertices and now it's not connected.
Good, so he's using connectivity.
Yeah, for removing vertices.
Yeah. Okay, no, I was looking for where it is used.
No, so I'm saying he used it because when he started, he removed vertices such that their neighborhood is a clique. Could do this because this preserved the connectivity. But after you get this subgraph, then you don't use it anymore. Okay, so this is one sufficient condition for rigidity in RD. And the second one is following theorem. Right. Theorem. So this is, so we showed it with Alan Lu and Eran Nevo and Yuval Peled. So now we are given a graph, maybe this two, give the graph. And suppose you have a partition of V into D parts. Of course, it's a partition, there are non-empty and they're disjoint. And so assume that if you restrict G to each of these VIs, you get a connected graph. And so I from 1 to T. And also, if you look at pairs, So you look at all the edges that go from Vi to Vj. And again, you get something that is connected. So if you can find some efficient, then G is rigid enough. And again, the first part of the talk, I try to convince you that it's very complicated or unachievable to find combinatorial characterizations of rigid curves, but here's like 2 examples where we have a very simple sufficient condition.
Does this relate to the being D-connected?
So that's a good question. Actually, when I wrote the notes, I said, okay, maybe is it possible that yeah. So I don't know.
What was the
So-
question again?
So if a graph is D times D plus 1 connected, maybe you can always try. I don't know.
About the relation between the two combinatorial.
Yeah, good question. I don't know. Okay, so the proof idea. So I want to tell you about the proof. And let me do some preparation. And the preparation is the following. So you remember the Jacobian that we mentioned a lot in this talk. So let's look at the normalized version. So this normalized rigidity matrix or RGP. So again, we have for every edge, we have a row. For every vertex, we have D columns. And here we have the edge ij. So in the ith, the D coordinate that correspond to the ith vertex, we put pi minus pj as before, but we normalize. And here pj minus pi. This is the matrix, and of course it has the same rank as the Jacobians. It's the same thing. So G is rigid. If you look at a specific embedding, you might have here 0 and you can't normalize it. If you think of rational function, then it's okay for any embedding. But let's say that if pi and pj are the same, then here it's just 0, vector of all scales. Don't know. So G is rigid in RD. Only if it's exactly with the Jacobian, so if the rank is R equals the n minus d. Okay, and Jordan and Tanigawa introduced what they call the stiffness matrix. Stiffness matrix of G in RD, which is just, so LGP is just 1 times the transpose, let's see, so RG times RG transpose. Okay. And so we have this matrix, we know that its kernel is the same as the kernel of RG transpose, so we know what to expect from the rank. And this
I said something about the statement. I just trying to understand. D equals 2, so you have.
if you can find it.
Why can't you just take 2 triangles and connect them by another edge?
So this is a sufficient condition and not necessary condition, but this thing is not rigid, right? And if you take this, so the graph between this and this is not connected because the vertices here.
Why not?
What do you mean? What is the graph between?
Now you restrict to the,
That's
so
what
G,
keeps the edges between Vi and Pj. It's
Yes.
always edges in each Vi separate.
Okay.
So there's only one edge between these
Okay.
vertices.
did I lose my notes?
But there is always.
I would look,
I think you
Oh.
can use this.
I mean, I can. I'm not sure that I see. Okay, I can use it without my note.
לא,
Maybe it's on
באיזה
this
מצב?
side. Maybe it's in the middle, no?
But okay, don't panic.
Yeah.
Again.
Favorite program, chop. Oh, wow. Okay. Open. זהו, זה הכל?
כן, שידפתי, אני כל הכבוד שידפתי את זה, זה היה ממש... אוקיי, תודה, thanks. Okay, so we know that I want to say, okay, so this is a positive semi-definite matrix, so we can look at its eigenvalues. So let's order them from smallest to the largest. And we know that we have here d plus, wait, so that I have my notes. D plus 1 choose 2 degrees dimensions in the kernel, so we know that lambda 1 equals lambda d plus 1 choose 2 equals 0. And G is rigid.
Are you taking it? This is our G times our G transpose or the opposite?
It's like this, but sometimes people are used to write this, isn't it?
If you, yeah, doesn't matter.
This
You
is
want-
why,
you want dn by dn.
this is why I wrote this, exactly. And I'm going to look at the opposite in a second, so it's important. So we know that G is rigid if and only if lambda d plus 1 choose 2 plus 1 is greater than 0. Okay, so this is what we are after, and Jordan and Tanigawa looked at this, actually at this, so they defined a d of G to be the supremum. So they actually looked at the value of this eigenvalue. Supremum of lambda d plus 1 choose 2 plus 1. Of course, it depends on the embedding P, so over all embeddings. And they cared about this quantity.
You need to normalize something, right?
They normalize, you normalize the matrix.
Yes.
All
I see.
the numbers are between 0 and 1.
Okay.
Minus 1.
So, but for this application, I only care about whether it is 0 or not 0. Okay, and I want to analyze this eigenvalue, and actually it will be more convenient. So for us, more convenient to look at what we call lower stiffness matrix, which is right L minus, which is maybe this, but which is the matrix dimension E. Okay, and here again, we know the direction of the kernel, we know what the rank should be, so we know that it is for the eigenvalue. And we know that we have many zeros, so lambda 1, lambda E minus Zn plus 3 plus 1 is 2. All of these are 0. And G is rigid if and only if the next eigenvalue is positive.
Maybe I missed something. Can you say something about how to think about this and what's the meaning of these eigenvalues?
So it's just like a way to capture the rank of this matrix. Other than that, I don't have an interpretation. It's just like something that helps us in the computation. Okay, so we know that G is rigid. Rigid in RD. And only if lambda m plus 1 exactly 0 when m is this number. Oh, this is m and m. Okay, note, let's write here m, and this will be +1.
If the number of edges is like expressed for minimally rigid, then it would be lambda 1.
Right. Okay, so now how to prove this theorem, so proof idea. We want to show a specific embedding, because it's enough, specific embedding where this lambda n is positive. And what would be this embedding? So I will show you the embedding for d equals 2, just because the matrix looks slightly simpler, but it's the same thing for any dimension. So the embedding is the following. So we have this partition, v equals v1 in v2. We'll look at actually a family of embeddings. So pt is the following embedding, where in R2, this is the point 0, 0, and this is the point t0. And for vertex I, if I is in v1, we embed it, the pi would be 0, 9. And if I is in v2, then pi would be t. So all the vertices lie on two parallel lines. 0, 3, 1, according to the partition that we got. Okay, and now I want to look at the matrix. So how does the matrix look like? So it's a family of embeddings because it depends on this parameter t. So I get family of matrices, but I can look at the limit. And if I see that in the limit, the eigenvalue is positive, then the continuity are also actual embedding for this eigenvalue is positive. Okay. So consider L minus limit still goes to infinity of L minus. Okay, so how does it look like? So I need to have each entry correspond to an edge. So let's look at all the edges between vertices in V1, edges between vertices in V2, and edges between one endpoint is in V1 and one endpoint is in V2. Okay, and the idea is that, I didn't tell you all the entries. And I'm a bit rushing because I wanted to show you another thing, but I guess I will not be able to, so at least slow. So why is it simpler? Because for us, it was simpler to work with this lower stiffness matrix. But it was easier to interpret the entries and control the entries because, so what is L? So LG. P, what is the entry that corresponds to E and E prime? So if it's the same edge, so the diagonal, and assuming that PI is same as PJ, we get 2. And if we have two edges that have a common vertex, E is IJ and E prime is IJ.
Will it be a detail? Or a 2x2 block? Or?
No, for each. No, so this is, so now I took the other direction, the transpose. I started with R transpose, and then I took R alpha. So here, this is essentially, so sometimes it will be 0 if some edge is, if Pi and Pj are the same, but in general, it's cosine of the angle between I, J, J prime. So this is the data. And otherwise it is 0. So again, there is some subtlety here. So if the embedding is taking Pi and Pj to the same point, here it will be 0. Okay, essentially this is what we get. Okay, so these are the entries of the lower stiffness matrix. Okay, now we can look at our embedding. I just put it in like two distant parts of the board. So what happens here? So if I have an edge between two vertices of V1, it will not interact with an edge with two vertices of V2. So I have some obvious zeros. So here I have 0 and 0. And the trick is that if I have an edge of V1, and a vertex here is also an edge of between V1 and V2, then I need to have there something, cosine of the angle between them. But when I take t to infinity, this angle becomes closer and closer to 90 degrees. And so cosine is 0. This goes to 0. So these parts, when I take t to infinity, so in the limits, they are 0. It's a trick. So in higher dimension, we'll have we'll have interaction between E V1 V2 and E V1 V3. But just to simplify it, I do it like that, but it's analyzable. And what do I get here? If I look at here, and this here, so I have cosine of the angle between, this is an edge and this is an edge. So it will be either 1 or -1, depending if the edges are like this, if it's 180 degrees or 0, it's either 1 or -1. And in the diagonal, we will have 2. So this is just like the graph Laplacian. So this is L1 EP. So not G, GV1. And here we get F GV2 in dimension 1. And here we get the V1V. So for the graph Laplacian, we know that if it is connected, then we know exactly that the kernel will have only one dimension. So we know how to count how many zeros we have in the eigenvalues. So number of zero eigenvalues. So we get here. So we need the rank to be the number of vertices -1. So you will have the edges minus V1 plus 1. This is the number of zeros plus the number of edges in V2 minus V2 plus 1 plus number of edges between V1 and V2 minus V2. And we get in total the right number. So number of edges minus 2 times the number of vertices plus 3. So these are exactly the number of 0 eigenvalues. And this is, so the next one will be non-zero. And this is the idea, to reduce this to the one-dimensional case and then use what we know about the Laplacian of a graph. Okay. Question about this?
Yeah, you look for counter examples, I mean, where it's
For the-
sufficient but not necessary, this.
Definitely, it's not necessary for complete bipartite graphs. You're okay. So the last part I wanted to mention some. I will not say much. I can mention some tries to use rigidity theory in combinatorial geometry. So, tool for. So can we use some ideas from rigidity theory and apply them in Erdős-type questions in combinatorial geometry? Why would I even think this might be possible? So here are examples of famous questions of Erdős. So Erdős asked, two famous questions are the distinct distances problem, distinct distances problem, and the unit distance problem. So the distinct distances problem asks the following: you have n points in the plane, and now you look at the set of distances that they span. What do I mean? So the set of distances that they span is simply you look at all the pairs, check the distance, and you write it down. So P minus Q distance for PQRT. So we consider here, if we have n points, we have n squared, or n choose two pairs, and we look at the set of distances. In general, if the points were generic, we would expect maybe all the distances to be distinct, but Erdős asks, can we choose a very specific P such that the distance set is much smaller than n choose two? And indeed, Erdős showed that you can find an example where the number of distinct distances span, oh no, never mind, only so Erdős gave an example where the number of distinct distances is small up to a constant, smaller than n over square root of log n. And Booth and Katz showed that this is distant again to a constant. It's almost solid. And why would I think that this might be connected to rigidity? So we see here that we have n squared pairs, but still we have only less than n distinct distances, which means that there are many repetitions. Maybe we can use the fact that we have many repetitions to find the same subgraph, and the same graph that appears again and again with the same distances, and then find some structure. Maybe I will not describe the unit distance problem. I don't have time. So many distances repeat. Can we find structure by using rigidity? So here is one instance where this idea was applied successfully. So we managed to, it was a work of Carl-Lambides, started a work of Carl-Lambides where we managed to apply this approach for a variant of the distinct distances problem using a variant of the rigidity question.
The aim here is to sort of give a new proof of Goose cuts the result, or what is the aim?
Not really, but it's like just trying to understand. So we have some specific problems that we think that we can approach using this. It's not specifically the distinct distances, but maybe one can. So I'll show you this variant of the distinct distances problem. So maybe not for the Booth and Katz problem, but at least for this instance, it worked. So I'll start with the description of this problem. So instead of, so we start with an algebraic curve in RD, irreducible. And we ask the same question. So now we have a set of endpoints on gamma, and we want to know, can the set of distances, or what can you say if you know that the set of distances spanned by P is small? What can you learn, or is it possible, or any question that you want to have this setting? And what is the variant of the rigidity question? So now you have a curve in RD, and here's a question. You have an algebraic curve, irreducible. So here's a question. Let's suppose that we embed a triangle on this vertex. Okay, so this fixes the distances ABC, and now the same question of the rigidity, only that we restrict to the curve. So can you find another copy of this triangle very close to the original one, if you want, that induces the same distances, but supported by the curve, of course. And since everything is algebraic, actually in this case, you can either find a finite number of copies of this triangle, or you can find a one-dimensional family. So you can move this triangle smoothly on the curve, or you just have a constant number. So if our curve is a circle, then you can do it for any generic triangle, and if it's a line, you can do it. But for dimensions 2 and 3, these are the only factors. So A3 is flexible on gamma, implies that gamma is, so again, so we know it in any dimension. So it's either a line or what Carl Embedding is called algebraic helix. Never mind what it is. But one can characterize the curves where this is possible. So it turned out that the curves where one can find a set P with small distances are exactly those curves. So for any other curve, the number of distinct distances will have to be large. If it is small, it must be an algebraic helix, and otherwise it will have to have at least n to the 3f distinct distances. Okay, so this is one place. Because everything is one-dimensional, we could kind of move from this problem to a generic problem. So we could use this thing, but if we try to apply similar ideas in the plane, we see that we have some difficulties. I know that I need to finish, so I don't know. Some obstacles are that, first of all, in general, our embeddings are not generic. And even if they are, even if we can look at a specific embedding and we want to check whether it is rigid, we get an embedding of a graph. We want to know whether it is rigid or not. We only have tools to check infinitesimal rigidity, but we are interested in actual rigidity. We care about the actual distances. So maybe the Jacobian will not have the correct rank, but maybe still we have the rigidity. So we care about actual rigidity. We maybe lose something by looking only at infinitesimal rigidity. So care about actual rigidity. Okay, so trying to go in this direction, I need one more minute. So in our work with Simonyi, we managed to show that if you have in R2, so in R2 we kind of have some tool. So we have a result that translates this question about rigidity into a question about line-line incidences in R3. And using this translation, we can show that if I have a graph G and I have a given embedding, and the only non-genericity genericity condition that I have for this embedding is that no 3 points lie on a common line. But other than that, I don't assume anything. On the graph G, I do assume a lot, so I assume that the number of edges is at least n to the 3s times some power of log n. If I have this, I can find a subgraph. So I find a subset of the vertices. V is of size at least 4. V prime is of size at least 4, such that if I restrict G to V prime, and I use the same embedding only for the vertices of V prime, I look at V prime, then this framework will be rigid. Is rigid. So I started with a given embedding, only assuming that no 3 points lie on a common line, and I found a subgraph where with this given embedding they have a rigid framework. And in the workbook progress, we managed to show that some other problem in combinatorial geometry can be reduced to this problem, but we need to know this result with less edges. If we have this result with less edges, we can use it in combinatorial geometry. That's all. Thank you. Sorry for taking time.
Questions?
Yes.
Okay, so the first example of a triangle, we learned it in 8th grade. Right, like it's edge, 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 if two triangles have the same edges.
First here or the first there?
First in the.
In the beginning.
Yeah.
Yes. Yeah.
Two triangles have the same edge, then they are overlapping, but then you also have edge, angle, edge, other types of theorems. You can ask about other rigidity when you don't necessarily know the length, but you know some lengths and some angles. And then you ask this.
I think you have something if you like fix the slopes of each edge, then it will behave more or less in R2 it will behave more or less the same. If you mix them, there are some variants, so I'm not sure if it was studied or not. I don't know.
Maybe it's a very specific question that I waited. Like this L method.
Yes.
Looking at like the some kind of like this R matrix is like looking at the vertex versus edge matrix, but we are maybe extending it by like instead of just putting ones, you're putting distances or something like that.
So you put the direction of the edge.
Yeah.
Yeah, so in one dimension it will be exactly 1 minus 1, and for other dimension it will be that you normalize it, so it's just the direction of the edge.
So by looking at this L matrix, it's like looking at the, I mean, it's looking at something that's connected to the Laplacian. And what I like about this proof is that you're looking at like the different directions. So I wondered if there was like a more general connection between like rigidity of a graph and rigidity of its line graph or something that like.
So our theorem doesn't only say that it's rigid, it also shows that the lambda m plus 1 is at least, you can look at the smallest eigenvalue here that is not 0, and it gives you some bound on the eigenvalue of the, of this L. So again, what is the question?
Okay, so does it like imply that also the line graph will be?
So the line graph, what do you mean by embed? So what do you mean by the line graph?
Yeah, so actually, I'm not sure actually. But I mean, you can ask about the line graph whether it's infinitesimally rigid or not.
So what is the line graph?
Oh, so like your vertices are now the edges, and you like connect to edges if they intersect.
Oh.
It's like something
Okay.
that I think that you get if you like just.
I see. I didn't think about it, so I don't know. Maybe it's obvious, but I don't know. I never considered it.
Think about the rigidity of the line graph. Is using the line graph as a tool to talk about the rigidity of the graph.
Yeah.
Yeah, I don't think it says anything about the line graph in terms of rigidity.
I mean, but isn't there a connection between the eigenvalues of the Laplacian of the graph and those of the line graph?
Yeah, but these are not
Right,
These are not the questions. I mean, this is meant to be a tool for a lower bound on.
sure, I didn't mean that it is supposed to as is say
Yeah,
something
no, I
that
didn't.
maybe.
Yeah.
Yes.
Maybe I missed it earlier. So in your proof for larger D, is the point set you consider so just D lines of points?
So you put the D, so you have D sets, the partition is for D sets, and you look at the D minus one dimensional, surface, linear subspace meant by the D minus one first quadrants, and you look here at a regular simplex with D vertices. And then you still have something that repeats. No, you will need to consider also what happens between edges that are here and here, but it's the same angle, so you can analyze it. The matrix there will not be block diagonal, but you can do something.
Okay, thank you so much.